This is homework 5, part B. We will be explaining a primary approximation used to calculate viscous loss due to frictional heating in non-circular pipes. We'll derive an expression for the frictional heating in relation to hydraulic radius of non-circular pipes. So to start this off, we will define what we know as our F. And that is going to be 4F L over D times V squared over 2. So from here, if we want to relate not by diameter, we can take that out and list that as a coefficient instead. So we'll call this HR, and that's going to be equal to diameter over 4. So that effectively gets rid of those, and that is going to be used for circular. So we need to redefine HR in terms of non-circular piping, and we can do that by estimating area over perimeter. All right, so from here, we will rewrite our F as being equal to FLV squared over 2HR. So this is our new frictional heating, and then we can relate this to hydraulic systems by making it set equal to Bernoulli's equation. That'll just be what we know as G change in Z plus our differences in velocities squared over 2, and then equal to our negative F. And our negative F in this case is going to be here. So instead of rewriting everything, I'm just going to erase this and make it equal to negative FLV squared over 2HR. So that is going to be our derived expression for frictional heating in relation to hydraulic radius of non-circular pipes. Okay, this is homework 5, part B, question 2. I have my iPad here for the question, so that's going to be, and the equations that we'll be using. So, I'm going to, cords everywhere. Hope it's falling. Okay. Well, okay, there we go. So for an open channel with rectangular cross section 4 meters wide, delivering 20 meters cubed per second of water at a 5-degree slope relative to horizontal, calculate the depth of water in channel. Use the Colebrook-White expression for free surface flow with a surface roughness of 5 millimeters. So we're in Excel for this one. My iPad likes to turn off, so I'll be reaching over and tapping it. We're going to start by defining our variables: theta, G, W, Q, rho, mu, the roughness, and the ones that we'll be changing are F and our H, and then we also are going to define what our HR is, or I'll move down a little bit, HR, our V, and then our Reynolds number, and then I'm going to label Bernoulli's equation as BR, and then our Colebrook's as CB. So running back up to the top, our theta is going to be equal to 5 times pi divided by 180. pi 180. What am I doing? Okay, 5 times pi divided by 180. Our gravity, as always, is 9.81. Our width is 4. Our Q is 20. Rho is 1,000. Mu is 0.001. This is going to be 0.005. This we can estimate at 0.05, and this just 1. So putting our equations in, well, first let's go ahead and formulas, create from selection. Okay. All right, so starting with HR, we have HW divided by 2H plus W. So we're going to type that here. That is going to be H times W divided by parenthesis 2 times H plus W. All right, so that's our HR. And then moving down to V, we get Q divided by H times W. So Q divided by H times W. And then our Reynolds number we can define as our rho times velocity times 4 times HR, all divided by mu. So rho times V times 4 times HR divided by mu. And then the longer equations, I always get a little bit tripped up here, so I'm going to pull this up. So it looks like we have G times sine parenthesis theta, and that's going to be minus our parenthesis. We're subtracting this whole thing. I'm going to add a couple extra parentheses just because I've been having errors with this. 0.5 times H, and that's going to be times this one I'm going to put in parentheses. 2 times H. Let's add a third parenthesis. 2 times H plus W. Oh, well, I added it because I wanted to put that there. Plus W divided by H to the third times W to the third. And then we can close that parenthesis and then multiply that whole thing, hopefully, by our Q squared. And then that should be the end of that equation. Oh, a typo. G sine theta minus F over 2 times H plus W divided by H cubed W cubed times, okay, I think that's right. All right, so then Colebrook, this one is going to be equals again with our parentheses, I'm going to do F to the negative 0.5, the inverse square root, plus 2 times log of how many parentheses do I need here? Times EPS divided by 12 times HR. Oh, escape, escape. I want to add parentheses here. EPS over, yeah, okay. Plus 2.51 divided by RE times F to the positive 0.5, I think. And then that should be all. Oh. Oh, I think it's mistaking things because I've done this a couple of times. Okay, that might have fixed it. Looks good. Looks good. Okay. Let's make sure these are correct as well. Just H and W. All right. So from here, we're going to do equals BR times BR. Oh, it's doing that again. Okay, well, I need to define these a second time, I guess. Okay. Equals BR times BR equals CB times CB. Okay, so from here equals this. And then we should be able to utilize our solver. Oh, except it's not that one anymore. It equals this guy. And then it's not this one anymore. It's these two. All right, let's see if this works. Well, times HR. Well, 0.05. I'm not really sure what's wrong with this. Let's see. EPS divided by 12 HR, 2.51 RE times F. Okay. maybe if I move some things out front, Q times Q times 0.5 times F. That should all be fine to not be there. And then you're also wanting, what am I looking at? Okay. G sine theta minus Q squared times 1/2 F times maybe it's this. Yeah, that's the numerator. That should be the denominator. Okay. Maybe we'll try again. Okay. Oh. All right. So that should be all for this problem. That gives us very close to 0. And then, I guess I can turn that off now. 0.025 and 0.8 for height. All right. All right. Question 3 of homework 5, part B, deriving an expression for optimal diameter of pipe based on annualized capital cost of CC times D times L and power cost of PC times P. Power is going to be our plumbing power. CC and PC are constants relating pipe dimensions and power consumption to annual costs, respectively. So we will be explaining how it is plausible for optimal velocity of water in pipes to have remained constant at 2 meters per second for many decades. To start this off, I'm going to write our total cost equation. So our cost is going to be equal to the given expressions so what we're going to need to do first is break down this power. We can obtain power by, well, I will write our what it would be derived from. So our G times change in Z plus this being equal to negative F plus the plus dWNF over dm. So from here, because we will be optimizing the system, we can actually cancel these and set the system equal to 0 because we want to obviously optimize what we're working with. And then we're going to actually relate this to power, so we have something that we can plug into this equation. So power we can relate to our work, our added work, so work from non-flow, by doing this. So from there, I'm going to divide and cancel. So what we're going to be able to plug into is our power divided by our m dot. So moving forward with this equation, we can actually move our negative F to the other side and say this. So solving for power again, because we want to plug something in here, we just multiply both sides by m. So that's going to give us our frictional heating times our mass is equal to power, the plumbing power of the system. Okay, moving forward with this, we're going to break this down. So our frictional heating we know as 4 FL over D V squared over 2. Simplifying this down a little bit, is going to be 2 FL over D times V squared. And then again, multiplying by mass. We want to break our velocity down into different terms. That's going to look like V being equal to Q over A. And then we're going to further simplify our Q as it relates to mass over density. So what is our area? Our area is going to be pi d squared over 4. So plugging that in and then using this here, we actually get a V that looks like this, which is 4 m dot over pi d squared rho. And then because we will be squaring it, I'm just going to square it before we plug it back in. And that will look like 16 m dot squared divided by pi squared d to the 4th rho squared. So plugging this back into here, we will obtain 2FL 16 m squared m all divided by d times pi squared d to the 4th rho squared. So simplifying this to more workable terms, we get 32 FL m dot cubed divided by d to the 5th pi squared rho squared. So this is a bit more workable. And I suppose the reason that we put everything into D, I should explain, is that we're going to be able to do the D cost with respect to the D. So again, solving, and that's because we want to make this equal to 0 when we take the derivative of this side. So doing that, we end up with 0 is equal, well, I should write this, CCDL plus PC 32FLM cubed divided by d to the 5th pi squared rho squared is equal to what we're taking the derivative to obtain a 0. So doing the derivative of both of these, this is going to end up equaling 1, so we can just write this as CCL. And doing the derivative of d to the negative 5th is going to be multiplying this coefficient by -5 and putting our d to the 6th here. So 32 times -5 is going to be -160 FL, everything else stays the same, d to the 6th pi squared rho squared equaling 0. Moving things over, we will actually get CC is equal to 160F, and then our L's cancel. So I'm just going to skip that step because it's easy algebra. FM cubed over D6 pi squared rho squared. From here, we can actually move this to the other side and replace it with our CC. I'm running out of room, so we're going to do d to the 6th being equal to I'm actually just going to do D is equal to 160 FM over CC pi squared, rho squared, and then all of this is going to be by 1/6 to get rid of our coefficient there and just be able to write it as D. All right, so to cancel our D and get that side equal to 1, we're going to relate our mass back to a term that involves D. Oh. Insert, sorry, blank page. Never done that before. So, again, as our mass relates to our velocity, we are going to be able to write that m is equal to our rho q or rho VA or rho V pi d squared over 4. So again, cubing this before we solve for here, or plug back in, that's going to look like rho cubed V cubed pi cubed d sixth, and then 4 cubed is 64. So this kind of looks like a 4. 6. So now we have D as being equal to 160F rho cubed, V cubed, pi cubed, d to the 6th, all divided by 64 cc pi squared rho squared, again to the 1/6. So we're actually going to be able to cancel our D, oh, geez, our D here by saying that that is D to the first power and then dividing both by D. So doing that, we are left with 1 equals 160, and also canceling both of these, and therefore these coefficients, and I guess this too. 160 F V cubed rho pi divided by 64 cc. Again, all to the 1/6. So if we multiply our 3 by our 1/6, we actually end up with 1/2. And then if we divide both sides by v to the 1/2, that is going to look like 1 over v to the 1/2, or v to the negative half, is being equal to 160 F rho pi over 64 cc. And if we multiply by -2 on both sides, cancel, we can actually solve v as being 160 F rho pi somewhere I dropped our PC, but our PC should still be in here. So PC, I won't go all the way back through, but 64 cc, 1/3. So from here we can make a couple of assumptions to explain how it is plausible or reasonable that our velocity is being equal to 2. So doing this, we can assume that our plumbing cost over our power cost and our capital cost as being 1. we can say that those are equal annual costs. And then we can also assume that the friction coefficient is around this number, and then that our density is equal to 1. I made these assumptions to see if it were plausible here. So working backwards, and then if you plug these numbers in, you can find that this is equal to 2 meters per second. So I'm going to box this in and call this one complete.